This is the Fibonacci sequence. It starts with 0 and 1, and each following term is the sum of the previous two terms. This method for calculating terms is good for most people, but the explicit formula is superior. It even has the golden ratio. How do you even come up with something like this? The answer lies in guessing and checking. We can check sequences that we already know well and see if they can become a Fibonacci sequence. Here, I'll show you what I mean. The first on the list is the arithmetic sequence. Very quickly, you can see that it falls apart. If we let A be the initial term and R be the common difference, this would be the sequence. We can check if this can satisfy a Fibonacci sequence by setting the sum of the first two terms to the third term. After some algebra, we figure out that A must be equal to R. Pulling out the next set of three terms, if we let A equal to R, we can simplify the expression to get that R must be 0. According to our first result, that means A must also be 0. Hence, our sequence reduces down to a lame sequence of zeros. Even though this does technically satisfy a Fibonacci sequence, we're looking for something a little less trivial. Moving on to geometric sequences, they seem more promising. Once again, letting A be our initial term and R be the common factor, we get this sequence. Setting the sum of the first two terms to the third term, it boils down to a quadratic. Solving this, we get that R can either be these two values, which conveniently can be written using the golden ratio. The golden ratio minus square root of 5 is also sometimes abbreviated as psi. Pulling out the next set of three terms, dividing by A times R on both sides gives you the quadratic from earlier. We know this equation holds because the values of R are specifically the roots to this quadratic. We can generalize this to any set of three terms in the sequence. Dividing by A times R to the n, we get the quadratic. Therefore, our sequence can look like either of these two sequences. Since A can be any number, we can just let it equal to 1. And so, these are two valid Fibonacci sequences generated from geometric series. To get to the standard Fibonacci sequence, we need to set some properties. First, the sum of two Fibonacci sequences produces another Fibonacci sequence. This is not very hard to conceptualize, and this example should be enough proof. Say you have these two Fibonacci sequences. If you add them together, you get another valid sequence. Moving on, since multiplication is just repeated addition, you should also be able to multiply sequences by some constant in order to produce another one. This is also very easy to conceptualize and can be shown through this example. Multiplying this sequence by 2 produces another valid sequence, which could have been produced by adding the sequence with itself. These two properties combine to allow you to take the linear combinations of Fibonacci sequences. This just means summing up multiples of Fibonacci sequences in order to create a new one. If it hasn't clicked already, we can construct the standard sequence by taking a linear combination of the two that we already know of. Essentially, it'll look something like this. Since we know the explicit formula for a term on the right-hand sequence, we just need to figure out what A and B are so that we have the explicit formula for the standard sequence. Since we only have two variables, we will only need to match the first and second terms on each side, since all other terms in a sequence just depend on the first two. Solving this system of equations, we get these values for A and B. Subbing these values into the explicit formula, we get this. Simplifying a bit further, we have the explicit formula for the Fibonacci sequence. This derivation was done only using algebra. Usually, it's derived using linear algebra. It's a good way to learn the applications of eigenvectors if you're interested. Thanks for watching, and I'll catch you on the next one.